Hello everyone and welcome to this next lecture on Python Power Electronics. Up till now I have been talking about just the concepts of switching, that is square wave modulation, pulse width modulation, all with respect to just a single inverter leg, and now I'm going to start with a three-phase inverter. So let's go over to the project folder. So this is the simulation package. Now I stopped here, alright. I finished square wave modulation, pulse width modulation. This is with a filter. So I showed how you can use a low pass filter to produce a sinusoidal voltage from a switching signal. Alright, like for example, example is this. We were able to use a high frequency switched voltage output using pulse width modulation as the output of an inverter leg. Just two inverters, an upper and upper switch, just two switches rather, an upper switch and a lower switch, and these two switches together produce a high frequency switched waveform, and you can use a low pass filter to produce a sinusoidal voltage at the output of the filter. Alright, this is a wonderful concept. Now let us expand this concept, and I'll show you what I mean by expanding the concept. So in this circuit we used just one leg of the inverter, because all I wanted to show was I wanted to demonstrate the concept of how you can use a static circuit like a power electronic circuit with only switches and diodes, no moving parts, to be able to produce a sinusoidal waveform. And in this, using these simulations, I've been able to show you how that's possible. With the square wave modulation, it is possible because embedded within that rectangular waveform is a fundamental frequency sinusoidal waveform. Only thing, there is a huge cost to be able to extract that sinusoidal waveform. With the pulse width modulation, because of the way we wrap the fundamental in a high frequency component, which is basically what is the concept of pulse width modulation. You have the fundamental, you have a high frequency, switching frequency, and because of that reason it becomes much easier to extract the sinusoidal. But this is not a practical circuit, okay, and I'll go over to what will be a practical circuit. Now at this stage there is one other folder, inverter voltage, and this inverter voltage contains two circuit files, inverter bridge.csv and inverter volt measure.csv. Let me just open this. So as you can see, now we have gone beyond the usual single inverter, single leg, right? Now what we have is three legs. So we have a single DC source, alright, and we have three legs. So there's the first leg with two switches, a second leg with two switches, and a third leg with two switches. And of course each switch has its anti-parallel diode. And every leg, the midpoint becomes one phase. So you see here, this is phase A, phase B, phase C. So we have now replicated that one inverter leg into three inverter legs and formed a three-phase converter bridge. This is what is called as a three-phase DC to AC inverter converter. It used to be called as an inverter, but now we call it as a DC to AC converter. So now the question is, how would you control this? And it's not very different from the usual method of how we control any other inverter. So the second circuit is just to measure the voltage. Alright, so this basically takes the output of the three legs and measures the voltage between them. So what you will get is a high frequency switched waveform between these three. Now to check out what happens in this, let's go over to inverter voltages, and you see there is a one single control file called inverter modulator.py, and it's almost the same as our modulate PWM.pi in the previous cases. Only thing now, we have the same carrier waveform rather, of high frequency 5000 kilohertz, 5000 hertz, not 5000 kilohertz. And later, the only difference is how do we generate the switching signals and how much switching signals do we generate. Now we have 6 switches, alright, S1 to S6. Before it was just S1, S2. So we need now 3 modulation signals, A, B and C. All 3 of them phase shifted by 120 degrees. And when you compare the carrier waveform with each modulation signal, you get the switching logic for that particular leg or that particular phase. This is the concept of 3-phase pulse width modulation. Now, I am not going to run this simulation. I will leave this as an exercise. Okay, so I would strongly suggest, please do try to create a simulation with these 2 particular files and check out the inverter bridge voltages. Alright, everything is there in this circuit. Everything, you have the circuit, you have the parameters, you have the control file, you have the descriptor file, everything. So all you have to do is just follow the usual procedure, add the circuits, process circuit schematics, view the components, upload the upload the parameter files, create the control, add this control file, upload the descriptor file, and you can run the simulation. So I would leave this as an exercise. Please do this on your own. What I'm going to do is I'm going to progress on to this next stage, and the reason I'm going to progress on to this next stage is this is exactly an extension of this previous one, and this contains a filter. So I'm going to talk about the same inverter bridge, but I'm in this particular simulation I'm also going to filter it. Alright, so let's have a look at what all we have here. The most important file here is inverter bridge. Actually, I can close the previous one because we're not using that anymore. So I shall close this. So here it's exactly the same 3-phase DC to AC inverter, DC to AC converter. Alright, 3 legs, each leg having 2 switches, each switch has an anti-parallel diode. Alright, this is our 3-phase inverter. Now let's look at what there are 3 jump labels, and these 3 jump labels go to this particular file called filter. Alright, now filter may seem a little complicated. Well, it's actually not. It is basically an inductor capacitor filter with an output inductor. So we have the same inductor. You see here there are jump labels because this is 3-phase circuit, remember. And these jump labels are connected to filter capacitors. So I would, if you find this confusing, just take a piece of pen and paper and just draw this on a piece of on paper. It's pretty simple. I am connecting a star connected capacitor bank with isolated neutral across these 3 phases. That's all I'm doing. Okay, so these 3 inductors along with these 3 capacitors form the 3-phase LC filter. Now, what is the reason for having this output inductor? This is actually, and this will be a later continuation where I'm going to talk about how 2 UPS units can be connected together in parallel and controlled in parallel. And for that reason, we will have an output inductor, because you need to control the current at the output. Okay. Now this can be removed for now. It's up to you, and you're welcome to do so. Please do try it out. So this is it. And finally, there is an output circuit. So let's go back to the directory and let's look at output. So this is our output. So output is basically just measuring the output voltage at the UPS. That's it. This is the 3-phase output voltage, and I'm measuring voltage across phase A and B, across B and C, and across C and A. That's all I'm doing. Okay, there's nothing much. Now there's one more circuit which you must add, and if you don't add, it's a problem, and that is bridge voltage measure. This circuit is just to measure the bridge voltage, that is the output exactly at the bridge. Let's look at this circuit now again. If you go to inverter filter, you will see here there are 3 jump labels. This is exactly the output of the inverter. Alright, these are the 3 legs. So these are the midpoints of each leg, and at the midpoint of each leg we have connected this circuit. So basically we are measuring the voltage across each leg. So we are measuring the voltage across leg A and B, B and C, C and A. The reason is simple. You can compare this bridge voltage with the filter capacitor voltage and see how these have changed. Okay, so anyway, enough talking, let me go and start. So first I shall cd into my folder, and first I need to activate my environment. Always remember the first thing you should do. Sorry. And this is a useful command. Just check which version of Python you have, just to know whether they're active. This bracket here, this is an indication that your virtual environment is active. That means my virtual environment Python 3 test is active. Anyway, so now that we are here, all I have to do is launch the circuit simulator. And everything is fine, so I just have to copy this link. And I just have to paste it here. So I'm done. Let me click on simulation library, and you can see this is where I stopped last. Single UPS filtered output with PWM. So let me create another one. Let's call this single UPS. Let's call this 3-phase output with LC filter. Okay, that's what it is. And I'll just copy it here as description. And let me get the path. Alright, so it's saved, no problem. And let's start adding the circuit. So first, most important circuit is the inverter bridge. Inverter bridge. And let's call this 3-phase DC to AC converter. Okay. Save this file. Everything is okay. Then we shall add the filter. Let's call this 3-phase LC filter. Also saved, no problem. Then we shall look at output, and we shall call this 3-phase output voltage measurement. Again, these descriptions are totally up to you. These are just what I'm using. Go ahead, use whatever you want, no problem. And last, we have to measure, we have to add inverter bridge. We have to measure inverter bridge voltage measurement. Okay, we are measuring the voltage across the 3 legs. So let's call this inverter bridge voltage measure, and let's save this. So we have all 4 files. This is all we have. So let's process the circuit schematics. And if you want to try this out, you're welcome to. You can try not adding one of these, or you can just click on one of these remove circuits and click on the process circuit schematics. You will see errors will crop up because now the circuit is not complete. Okay, let's come back, and here you see the circuits do not have any detectable errors. Always scroll down and check. If there are errors, they will be listed here. Okay, let's go back to the main page. Now you can edit the circuit schematics parameters. So first, bridge voltage measurement. Let's click on view components and let us upload the file. There is a parameter file, just upload it. And you see they've all been uploaded. It's nothing much, just 3 voltages. You're just updating the voltage level to 600 volts. Then comes inverter bridge. And we can choose inverter bridge params.csv and upload this file. And you see they've all been updated. Everything is 600 volts. The resistors are 0.01. Everything seems okay. Yeah, DC voltage is 450 volts. That's no problem. Now comes filter. And in filter, all I have to do, inverter filter.params, upload file. So you see, yeah, they have changed. Inductors are now 0.01 millihenry, capacitors are 100 microfarad. This is the usual values that we have. We are using the output inductor to be 400 microhenry, but then again this can be reduced. Quite often it is reduced to like 100 microhenry also. And that's it, we are good to go. The last is inverter output voltage measurement. And these just 3 voltages, voltmeters rather, not voltages, 3 voltmeters. Let me upload the params file. And it's done. You see the voltage levels are updated. Let's go back to the main page, and this time let's go to control. And let's check out what the control is now before we do so. Inverter voltage is filter, and you see there is only one in .py file, .py. This is the control file, and this is the pulse width 3-phase pulse width modulation. So we have only one control file to add, and we just go, it is here. So we say 3-phase PWM. Configure control, you just upload the descriptor file. So inverter modulator.py, inverter modulator underscore desk.csv. Upload and click on this. So we come down, there is all these, good. So all the variables have been populated. With this, we are now ready to run the simulation. So let's click on the run button. As your files become larger and larger, these simulations will take more and more time to solve. So as always, let's go over to the terminal and check if there's any cryptic error. No, there isn't. So it is indeed running. So to check whether it's really running, it's always best to immediately add a plot. And let's call this output filtered output voltage. So let's look at the final output voltages. And when I mean final, it means this one after the filter. Alright, so let's add these. So it's inverter B, inverter 1 cap A B. So let's call this AB, or rather call this VAB. Save waveform. Inverter cap BC, VBC. Save waveform. Yeah, and I forgot to tell you, as you add waveforms, it will tell you what waveforms you added and how they are. So for example, it shows you voltmeter inverter 1 capacitor AB is mapped to the variable VAB. So this is how it will show up in the plot. And finally there is CA, that is PCA. And let's click on done, and we have the first plot. So let's click on the plot button. Let's go over to my directory. And you see, you get, it looks weird, and the reason why it looks weird is because of the inductor capacitor, and it is still in oscillation. So the only way to really do this is, at least now that you see this, what is important is you don't see all zeros. If you see all zeros, it means something is not connected. Some control output is not connected to a device or something of that sort. If you see 10 raised to 27 or something like that, it means your system is unstable. This means your system is actually running. Okay, so there is hope. Okay, so what I'm going to do for now, I'm going to pause this video and I'm going to come back in a few minutes when this is done. So stay tuned and see you soon. So now that the simulation has been running for a while, let's try to plot it again. Alright, something's happened. And we have a new plot, filter output voltage. So you see here, initially these are the oscillations which were produced because of the inductor capacitor filter, and because it's a three-phase circuit, they have interactions between each other also. But after a while, you see here, it becomes a lot more stable. So let me plot 0.25 to 0.27. Let me do a zoom feature. So that is 0.25 to 0.27. Remember here, the plot range has to be something that's valid, or otherwise it will just plot the entire range. So yep, so these are the voltages which you get, or rather the filtered voltages. As you can see, these are sinusoids, they are balanced, they have some amount of harmonics, alright, but this is what is most important. Let's now also plot the bridge voltage. Let's call this inverter bridge voltage, and let's plot the voltages. So that's inverter 1 bridge AB. If you have a doubt ever, just go over to the schematics and check the actual names of the components. Oh, that was a mistake. So now there's no way to rectify a mistake like this. That's the unfortunate part. There's no edit waveform. Let's plot how it is. If it's a problem, we'll just have to delete it. So you see here, these are the bridge voltages. Not very clear, and actually this red line is even disturbing. The straightforward thing is, let's just delete this plot and plot it again. So you see what I did here, I made a mistake. I added this fourth waveform which is completely non-necessary, but it was a mistake and there's no way to edit it, so we just have to delete it and add it again. So we should just say inverter, and there's a in the future releases I might add an edit option. Well, I probably should actually. Because in large circuits the room for error is fairly large. You do tend to make mistakes when you're building large circuits. So anyway, this time I got it right, and let's plot it. And it seems to have done something. I got a plot, and yes, this time at least that red line is gone. So let's plot, let's zoom in between 0.25 and 0.27. So that is here. Remember, you must add the range in the plot which you want. All right, you can't add the range here and plot this one, that won't work. Okay, something is done, and let's look. Yeah, so we have three voltages, VAB, VBC, VCA, and it's hard to notice here, but these are because these are like highly switched waveforms, but these are actually three-phase voltages phase shifted by 120 degrees, and that's why it's coming out like this. It's very hard to notice it, and particularly because of the color combinations and one superimposing the other, but this is how it is. Now let's contrast that. Let's plot this filter output voltage again. And this is what you get. So I'm just zooming in here, it's pretty coarse, but okay, I guess I could zoom in between 0.2, 0.3 and 0.32. Let me zoom in. Alright, so you see here it is much smoother, because now what's happening is with time the oscillations die out. Okay, these oscillations, those glitches in the sinusoidal waveform were mainly because of the inductor capacitor oscillators that were being formed, and with time these oscillations die down, particularly when the inductor and capacitor are not very large. And when you have PW modulation, that's the advantage. You don't need very large filter parameters, and when you don't have large inductors and capacitors, they don't form strong oscillatory circuits. So these oscillations will die down, and as you can see, these are now fairly smooth sinusoids. So let's compare that with what we have here. As always, the main thing about simulations is always compare waveforms. This gives you the best idea of how a simulation is performing, the effectiveness of a circuit, things like that. This is the output voltage at the bridge. Okay, now if you really do an analysis, it is a three-phase balanced, rather well balanced in the sense, I don't know how you would say, because there's a high frequency harmonic, but otherwise it is balanced, three-phase balanced AC voltage. Alright, that's what you get here. Only thing is there is a high frequency component, which is a 5 kilohertz component in all three of them. And after you filter them, this is what you get. Alright, a three-phase sinusoidal voltage. So now, this is the importance of this particular simulation. Now, before we showed how you can have a single inverter which is switched by pulse width modulation, you can achieve a sinusoidal waveform. Now, in this simulation, what I'm showing is you can have three-phase modulation signals, and those three-phase modulation signals fed to a three-phase bridge will produce a three-phase balanced sinusoidal voltage. Isn't this absolutely fantastic? This is the effectiveness of power electronics. This is how power electronics works. Alright? You do not have a rotation machine. You do not have three-phase windings. You do not have any of those things. All you have is these 6 switches. And nowadays, you can actually have these 6 switches in a very compact package. What is called as an intelligent power module, or inverter modules, converter modules, several of them. So, this is how effective this entire technology is. And this is how we are going to use this concept in producing a three-phase UPS that produces balanced sinusoidal voltages that are regulated. And that can be applied to a sensitive load which needs regulated voltages. Like a sensitive, when I say sensitive load, it could mean a data center, it could mean a server, it could mean an induction motor, it could mean a ball crusher, or some of those special kind of machines which need very special, very well regulated voltages. So this is how we will be producing it. Right now, I'm going to end this lecture now. Again, in the next lecture, I will talk about how. No, this is open loop. Okay, I'm just taking 3 random modulation signals. Now we need to regulate them, and to regulate them, there is a 2-step method. All right. The first step will be controlling the output current. The second step will be controlling the output voltage. So that's what I'm going to show. The next step will be how do you regulate the current that is produced by this inverter. All right. So that's all for now. And if you have any doubts in this lecture, please do email me or message me. If you don't, just wait for the next lecture. So thank you so much for watching, and see you soon. Goodbye for now.